Okay, this video is intended to explain or help understand the connection between the graph of a rectangular function and the graph of a polar function. In a rectangular function, we have an input value x and an output value y with, and I'm going to use some trigonometric functions, which is why I've got the x-axis labeled in units of pi. But the input is the x-axis value, and the output is the y-axis value, or the y-coordinate. So suppose we have the simple function y equals 3. Okay, well, on the rectangular, on the coordinate plane, rectangular coordinates, that's just a set of points. Every point on the coordinate plane that has a y-coordinate of 3, which just forms a horizontal line. Now, the polar, when we're graphing a polar function, now it's not y equals 3, but the output is r. The input is the angle, and the output is r, so the equivalent function would be r equals 3. Every point on this polar coordinate graph where the radius is 3 units from the pole, 1, 2, 3. So here's a unit, here's a point where the radius is 3. Here's another point where the radius is 3. Here's a point where the radius is 3. It's just a circle on the polar coordinate plane. Boom. This is the equivalent of the polar equivalent of y equals 3. Now, what if we had x? Let's say x equals pi halves. Okay. Every point on the rectangular coordinate plane that has an x coordinate of pi halves. Here's a point, pi halves 1, pi halves -1, pi halves 0, etc., pi halves 3. Every point on the rectangular coordinate plane with an x coordinate of pi halves creates a vertical line. What happens on the polar coordinate plane if you restrict the input to a specific value? Theta equals pi halves. Well, on the polar coordinate plane, we have the angle 0. Here's the angle pi sixths. Here's the angle pi thirds. Here's the angle pi halves, that angle right there. So a point right here would be where the angle is pi halves and the radius is 2. Here the angle is pi halves and the radius is 1. Here the angle is pi halves and the radius is 3. Now it just occurred to me that you might make a, let's change this to, let's move it back a little bit, to pi thirds, okay? Because I don't want you to make an assumption that pi thirds. So here's the angle pi thirds. This angle right there is pi thirds. So this point would be where the angle is pi thirds and the radius is 2. Here, the angle is pi thirds and the radius is 3. Here, the angle is pi thirds and the radius is -1, and so forth. Here, the radius is -2, but the angle is still pi thirds. We're still standing on the pole looking out at the pi thirds here, and backing up 2 units would be a radius of -2, an r value of -2. So the polar coordinate system, the polar coordinate equivalent of input restricted is also a straight line, but it's a straight line that maintains this certain angle theta. Okay, now we're going to jump in complexity here quite a bit. We're going to jump to the rectangular function y equals 2 plus the sine of 3x, and we're going to relate that to r equals 2 plus 3 times the sine of theta. Okay, first I want to get a look at the graph of y equals 2 plus 3 times the sine of x, a complex function. So the first thing that happens to this input is we're taking the sine of the input, and then we're multiplying that sine by 3, and then we're adding 2 to that input. So if we take the input of 0. Sine of 0 is 0. 0 times 3 is 0, and 0 plus 2 is 2. So that gives us the point 0, 2. So here's one point on the graph, 0, 2. Okay, now let's do the same thing with pi halves. The sine of pi halves is 1. 1 times 3 is 3. 3 plus 2 is 5. So that gives us the point pi halves 5. Oops, that's pi halves 4. Let's try that again. Pi halves 5. And now let's substitute pi. I'm getting 5 key points on here. So it's input pi. The sine of pi is 0. The output, when the input is pi, the output's going to be the same as when the input is 0. So we're going to have an output of 2 again. So that gives us the point pi 2. Okay, now we put in 3 pi halves as the input. 3 pi halves. Sine of 3 pi halves is negative 1 times 3 is negative 3 plus 2 is negative 1. That gives us the point 3 pi halves negative 1. And then when we substitute 2 pi, when we use the input of 2 pi, we're going to get the same output. Oh, I'm really OCD with my back colors. When we use an input of 2 pi, the output is going to be the same as it was at 0 and pi, and that's an output of 2. So that gives us this point here. And you can kind of picture the graph doing this. And I'm actually going to try to kind of cheat here. Kind of give myself some symmetry. Flip it left to right. And then I'll take this whole thing and flip it up, down to connect my points. Okay, so that would be one period of this function, and it would repeat. Okay, so now I'm going to take this graph and let's see if we can correspond it to the polar function. R equals 2 plus 3 times the sine of theta. Okay, so this starting point, 0, 2, that's going to be a starting point where theta, the angle is 0, and the radius is 2. Well, that would be this point right here. I might as well use green like I was before. Now, when theta is pi halves, y is 5. Not theta, when x is pi halves, y is 5. That means when theta is pi halves, that's right here, pi halves, r, the radius, is 5. 1, 2, 3, 4, 5. Now, here's the thing. R, the y coordinate increased from 2 up to 5. So the radius is going to increase from 2 up to 5. Something like that. 5 is where it maxes out. And then the radius is going to come back down from 5 back down to 2 by the time theta equals pi. So when theta equals pi, that's right here. We're going to have another point where r equals 2 again. But this radius increased from, flip left, right, and let's turn it into blue to correspond with. So the radius increases out to 5 and then decreases back to 2. Now the third section, when x equals 3 pi halves, y equals negative 1. That means when theta equals 3 pi halves, as here, y equals negative 1. Oh, I should say r equals negative 1. So that would give us a point right here. If theta is 3 pi halves, looking straight down, we have to back up 1 unit for a negative r value. So how does r decrease? Notice we have an x-intercept. X equals y equals 0 when theta is, I'm thinking that's going to be pi sixths after, like theta plus pi sixths. I'm thinking that we're going to go, so this little piece right here, when y decreases from 2 to 0, y is going to decrease from 2 to 0 like that. R decreases from 2 to 0. When r equals 0, you're on the pole. And then r becomes negative to -1. That's what creates the little loop inside the cardioid. And so then r, we duplicate that coming back up, y coming back up to 2. So I'll try a new color here. R coming back to 0, y coming back to 0 would be r coming back to 0. From -1 back to 0. And now we're into the fourth quadrant. These points, this purple and that piece of, this purple were our third quadrant inputs, the purple. Now the orange is going to be our fourth quadrant inputs from 3 pi halves to 2 pi. And so 3 pi halves to here gets us back to r equals 0, and then r increases from 0 to 2 again, and that's going to be like that. And that's where we get the shape that we get from this polar function. And it corresponds r increasing and then decreasing and then increasing again. R increasing. Actually, let me this a radius. Okay, so here's a radius. The radius is getting longer and longer and then shorter and shorter. Shortens back to 0, backing up to -1, and then coming back to 0 and increasing back to 2 by the time we make the full cycle. And that's hopefully a good visual for the connection between the polar and rectangular function graphs.